Okay, so I think we can start now. I explained already last time that the first topic we are going to talk about is chapter 11 in our textbook. We will spend roughly 4 weeks discussing chapter 11. Now, maybe just to give you an overview of what we want to do. So I guess in high school maybe you have at least briefly touched upon the topic of series. So what we want to discuss in chapter 11 is in more details is this theory of series, and one of the goals we have eventually is we have already discussed last semester functions like e to the x, but we know that such functions, or let's look at ln of x. We know that our definition of this function was using this integral here. Now, this does not really explain how for instance, the calculator, if you take the calculator, you know that the calculator is able to compute ln of x if you give for a given x, but obviously the calculator is not going to use this kind of definition. So this does not explain how the calculator is able to compute the ln for certain values. Now, one of the main goals in chapter 11 is to understand how the calculator can compute functions like this, functions like ln or e to the x and so on. So we will make more precise. These functions you have learned already in high school, and then you have used the calculator in order to compute them. That's why you understand these functions. But in this, one of the main goals of this chapter, there are also others, but one of the main goals of this chapter is to understand how the calculator is going to do this. But we will still need some 3 weeks in order to understand this. So first we have to look at the theory of series in more details. And we will start with chapter 11.1, which is sequences. This is actually something we have discussed already, or which I have introduced already when I was introducing the Riemann, when I introduced the Riemann integral in chapter 5. But I will recall this. You all know what a sequence is. So a sequence essentially is a list of number. This is one way to look at the sequence. Another way to look at the sequence is apart from looking at the sequence as a list of number, you can also say a sequence is a function. Namely, you have a function which maps n into the real numbers. So this is another way of looking at it. So sequences are either a list of number or a function, with the special case where the domain is equal to the positive integers. Now, you also know that the terms of a sequence we are going to call, so the an we are going to call the nth term of a sequence. And what we want to do first is we want to look at such sequences. Now, there are different ways normally to describe such sequences. One way is you just write down the first few elements, and then from the elements, normally by looking at the elements, normally you know how the sequence will go on. This is one way to do it. Another way to describe a sequence is you give an expression for an, and we will also use the notation. So these are different notations which are normally used for sequences. So sometimes we write a sequence, we just describe the terms. Of course, this is kind of dangerous because it might be uncertain how it's going on. But if it's clear how it's going on, we will use this kind of description. Another way is we just give a formula for an, or we also use sometimes this notation here. So this is just notation. Okay, so some examples for sequences. For instance, an easy example would be, 1/2, then 2 over 3, 3 over 4, and so on. So this would be the first, correspond to the first notation where we just describe the terms. But you actually see here immediately that normally you see here that the sequence starts at 1. This is not necessarily true for all sequences. We can also start at 0. This doesn't matter. So here if the sequence an starts at 1, then we can describe it like this here. Or we will also use this notation here. Okay, now another sequence would be, okay, if I describe it like 1, and then I have minus 1/2, and then I have 1/3, minus 1/4, and so on. So here an is equal to minus 1 to the n plus 1, 1/n. Or we use this notation here, so minus 1 to the n plus 1, 1/n, and n from 1 to infinity. Okay, you know already from high school that sometimes sequences are not given like this. Sometimes sequences are given by so-called recursive formulas. So the most famous example for such a sequence is the so-called Fibonacci sequence. I'm not sure whether the spelling is correct. Okay. Now, this kind of sequence was introduced by Fibonacci long ago, and actually this is a simple model for the growth of a population of, for instance, rabbits. So at time point 0, you have one pair of rabbit. So at time point 0, you have one pair of rabbits. Now, rabbits normally. So the model you use is that if you wait, so this is time 0, if you wait two time decades, then the pair of rabbit is getting productive. So will produce two kids, which is also another pair of rabbits, and they will get productive again after 2 time periods. So this is the easy model, and of course you have an assumption which is not satisfied in reality, namely the rabbits never die, so the process will go on forever. Now, if you have such a process, so at time 1, okay, you still have one pair of rabbits because they are not productive yet. Okay. Now at time 2, now this pair of rabbits is getting productive. So if a pair of rabbits is productive, I will denote it by orange circle. Okay, so now they are productive, so they will produce one pair. Okay, so at time point 2 you have 2 of them. Now at time point 3, okay, so this one is productive. Okay, this one is not productive yet, and this one will produce for this time point another pair. And now the situation at time 4 is okay. So again, this is already productive. Now this will also get productive now because we have waited 2 time decades. So this one will get productive as well. So we have 2 productive pairs, and then you have one which is not productive yet, and both of them produce one pair. Okay, and now you see already the rule. Because you have, if you reach time n, you have to look at okay, how large is the population at time n minus 1, and you have to, because all those will form a part of the population at the next time, and you have to look at how many are there at if you look at time 4, at time 2, because all of them will be productive at time 4. Okay, so from here you see already that the recurrence. If fn denotes the number of pairs after time n, then you will have this is equal to fn minus 1 plus fn minus 2. And essentially this fn minus 2 comes from the rule that you have to wait 2 time decades that the pair is getting productive. Okay, this is for n larger or equal than 3. I guess you have heard this in high school. Now, and we have also initial conditions. F1 is equal to 1 because the time point, I should say, because I started here at time point 0, but okay, I don't want this, so I denote this. I shift the time point to 1. So what I denote here by 1 corresponds here to time 0. So f1 is equal to 1 and f2 is equal to 1 as well. Okay, and this way of describing a sequence is called you describe the sequence by a recursive relation. So this is called recursive relation. Okay. Now the first obvious question here would be, okay, so this produces obviously a sequence 1, 1, and then you always look at the previous 2 and you add them 2, 3, 5, 8, 13, 21, and so on. And now the obvious question is, okay, can you give an expression for f of n? Okay, is it possible to write a formula like f of n is equal to, and then some expression? Now here for this case, it's not really obvious. Or can someone guess it? You see, it's not really obvious. Okay. Sometimes you know that in some journals you find this kind of exercises. Okay, you have a sequence, try to find the law for the sequence. Now for this one, it's tricky. Okay, and the answer is not very simple. Okay, I tell you the answer is 1 plus square root of 5 to the n minus 1 minus square root of 5 to the n over 2 to the n square root of 5. Okay, so maybe this is not so easy to guess. Okay, from this relation here. So you see, and you see in particular this relation is much more simpler, because if you look at this here, if you just look at it for the first time, it's not really obvious that what you get here, because it's kind of complicated. But essentially for all n, if you plug in a n, what you get is a positive integer. Okay, it doesn't look like this because you have your square roots. Okay, but using the binomial theorem, you see that this easily reduces to an integer, and you can check that what I claim here is true just by plugging it in this relation and showing that this verifies this relation here. This is a famous formula called Binet's formula. We will later on we will also understand how to derive this formula from this recurrence in a systematic way. So there is actually a way how to find this formula. But later on we will understand how to do this. Now, okay, so this is one example for a sequence which is given by a recurrence. Fibonacci sequence. Another obvious example would be, okay, here you compute the next term by looking at the previous 2. Another obvious sequence would be, or another obvious way to generate the sequence is you look at the previous 3. Okay, so you start with 1, 1, 1, let's say, and then you always add the previous 3 ones, 3, and then you have 5, and so on. Okay, so the recurrence which you then have is, let's say, an is equal to an minus 1 plus an minus 2 plus an minus 3. Okay, and this is for all n larger or equal than 4. And you have the initial conditions a1 is equal to a2 is equal to a3 is equal to 1. Would be another sequence. Now, because this is the Fibonacci sequence. So this also, maybe you've learned this in high school as well. I'm not sure. This is also a name. It's called Fibonacci. Actually, the name is just a combination of the name Fibonacci. You see, you take this here. This is coming from Fibonacci, and you add another this 3, which means 3, which is the Greek word for 3. So this is another sequence, and you can go on. You can also say, okay, I do not just look at the previous 3. I look at the previous t ones, add them. Also such sequence occur in applications, but this Fibonacci sequence is more easily explained. But these are other sequences, and again you have here the same question. Okay, is it possible to find such an expression for an? Certainly complicated. So you see, we have essentially two ways of describing sequences. The first way is you just give an expression for the nth term of the sequence, and the other way is you give a recurrence. Here you see that for this, the recurrence is much more simpler in some sense than this formula here. So kind of this is preferred here. Okay. Okay, now let's maybe go back to my first example, this one. Okay, so this sequence. Now, if we plot the terms of this sequence, so the first term is 1/2, 2/3, 3/4, and so on, then you see that, okay, this is 0, this is 1. So the first term will be here. Okay, then the next one will be closer to, should be closer to 1. And then you see, if I really plot the terms, I will get closer and closer to 1. So it seems like it seems like this sequence as n tends to infinity approaches 1. So we see that we naturally have something as the limit for sequences. Actually, this is something we already. This is not new for us. If you look at chapter 11, 11.1, the definition of a limit for a sequence is given there. But actually, it's in our textbook. It's used much earlier because when we looked at integrals. Integrals is also a limit of a Riemann sum, and the Riemann sum is the Riemann sum is also a sequence. So here we already looked much earlier at limits of sequences. But just to give the precise definition once more, now we say that we write that the limit of a sequence as n tends to infinity is equal to L, and this means that now the precise definition we know involves the epsilon delta definition. So roughly speaking, it means that as n is getting larger and larger, an will be closer and closer to L. But using the epsilon delta definition, this means that for all epsilon, okay, so whenever we look at, so we have here L, whenever we look at some epsilon interval around L, then we will find an index n which might depend on epsilon, such that okay, most of the terms, almost all of the terms, will fall into this epsilon interval, namely for all n larger or equal than n. This kind of means that for every epsilon, okay, if you look at such epsilon intervals, then if you count how many of the terms of the sequence are outside this epsilon interval, then you have only a finite number. So no matter how small you choose the epsilon, you will always find an infinite number, even more than infinite number. From some index on, all elements will be inside the epsilon interval. Okay, so but we are already used to this actually because we have defined limits already for functions last semester. Essentially, we use the same definition, same motivation behind it. Okay. Now, if the limit exists, we will call the sequence convergent. Otherwise, the sequence will be called divergent. So if the limit of a of n as n tends to infinity exists, then the sequence is called convergent. Okay. Otherwise, it's called divergent. Okay. We know there are several different ways, if you compare the situation with limits of functions, we know that there are different ways how a sequence can fail to be convergent. But one very particular way is that as n tends to infinity, an is getting larger and larger. And in this case, we say that the limit of an as n tends to infinity is equal to infinity. It's just the same as for functions. So we have a similar definition. for this here. So this actually means that the sequence an is divergent. Okay, but the divergence is very special. Namely, as n is getting larger and larger, an will also get larger and larger. So in other words, for all bounds, large bounds, okay, you will again find the n, which might depend on m, such that our sequence will be larger than m, will be above the bound for all n larger or equal than n. So okay, this is the precise definition that that a limit of a sequence an is equal to infinity. Sometimes in some textbooks, but not in our textbook, this case is also included in the notation of convergence. So also in this case, if we consider this kind of a number, okay, we will say, okay, also this case would be called convergent. But not for us. So this means divergent, but divergent in a very specific way. Okay, now this is actually the same as for limits of functions. The first question, as for limits of functions, I will just roughly explain this. This is what you find next in our textbook. Okay, how to figure out for certain given a sequence, how to figure out that the sequence is convergent or not. Now, essentially, if you have such a definition, what you have to do is you have to check the definition. But as we know from last semester for functions, this is kind of not so convenient to always go back to the epsilon delta definition. So the approach we used last semester, just to remind you, is okay. First, we figured out limits of simple functions, and then we used some building rules. And essentially the same we will do here. So this is essentially what you find in our textbook next. But in order to quickly find some easy examples, it's first, it pays off to try to figure out whether there is some relationship between the limit of functions and limit of sequences. And actually there is a quite convenient tool which will help us already to identify limits of many sequences, namely the following one. Now this is something I also explained already last semester. This is just to remind you. Okay, if you have a function, okay, assume you have a function f of x and assume that this limit exists. So now for our function, this is like the definition of the limit last semester. Okay, assume that you define a sequence by evaluating this function at the positive integers, then it's like I guess everyone will believe me that this relation will hold as well. So if you know that the limit of f of x as x tends to infinity is equal to L, and you define a sequence like this here, so this is a definition, then also this sequence an will be convergent, and the limit will be the same as this limit here. Okay, so this is something quite obvious, but you have to, in order to prove this, I'm not going to prove this, but you can try to prove it on your own, because it's kind of here you have to use the epsilon delta definition here for sequences, and here's the epsilon delta definition for functions. It's a little bit, it's not complicated, but you have just to write everything down precisely. Now, and the inverse, I just want to stress, it's not true. Okay, the inverse here means that given a function f of n, you define a sequence like this here. If you know that this limit here exists and is equal to L, this does not mean that this limit here exists. Okay, it's quite obvious. Who can give me an example? Or maybe I tell you. Okay, so for instance, for this one, if you look at this example, okay. Now, what is our sequence an? 0. Okay, so this sequence here will have a limit, but not this one. Okay, so the inverse is not true. Okay, now you might wonder why I'm going to stress this. This is actually quite convenient, okay, because now we have last semester we have already figured out, or we understand very well how to compute limits of functions, and this will help us to find corresponding theorems for sequences. So for instance, if you look at the function f of x is equal to 1 over x to the r, with r is larger than 0, okay, then we know already that the limit as x tends to infinity, 1 over x to the r is equal to 0. Okay, so we can use this theorem here, and we see that the limit as n tends to infinity, 1 over n to the r is equal to 0 as well. Okay, so this seems to be trivial, okay, because in high school you have already learned this, okay, but this is just because our definition of this limit is the epsilon delta definition. Now, if you want to prove something like this, okay, you should use the epsilon delta definition, but you can avoid this if you prove first this and then just use what we have done last semester, because then immediately you get some results like this here. Just to stress this point. Now, so this works already. This is already helpful for quite a lot of sequences or limits of sequences in order to figure out whether the limit exists and to compute it. You just try to find such a function, and then you use the theory which we have developed last semester, and that's it. But you see that, for instance, does not work. This does not work for this one. Okay, for this one it does not work. You cannot use this result here. Okay, because what would be the function? Okay, you have to find first the function which and the function evaluated that the integers should be equal to this sequence here. Okay, now you would guess this one, right? But this does not make sense here, because we know that the exponential function, okay, the a must be larger than 0. Okay, so for instance, here, okay, what is this here? Okay, so you cannot look at this function here. So actually, for this simple sequence, which looks pretty similar to, if you forget about this one, okay, you cannot use this result here in order to figure out whether this limit exists or not. But of course, what you could do is you use the epsilon delta definition. Okay, you just use the epsilon delta definition, try to prove it. Okay, but not very convenient. So there is actually another a better method to handle such sequences. You find this theorem in our textbook as well. So there is another result. If you know that the limit of the absolute value of an as n tends to infinity is equal to 0, then this will imply that the limit of an as n tends to infinity is equal to 0 as well. Okay, actually this is in both direction. Okay, and this is kind of helpful, okay, because this tells you, for us the important direction is this one. Okay, because this tells you that okay, if you have something like this here, okay, it is enough to look at the to take absolute values. Okay, so you can forget about this minus 1 to the n. Okay, so you see that you can look at this you can look at this limit instead of this one. Now for this limit, we can use the theorem I just told you, which we just have seen that this is equal to 0. And now you use this result here, and you get that this limit here exists and is equal to 0 as well. Okay. So this is helpful here for sequences where you encounter such phenomena here. Okay, so essentially these two theorems help you to, so this theorem and the theorem I showed you before help you to figure out limits of some easy sequences. And then as in the function case, what you need next is some kind of rules to build. Now, all the limit theorems, you find this in our textbook, all the limit theorems we have learned last semester will hold for sequences as well. And moreover, also the squeezing theorem will hold for limits of sequences as well. So I'm not going to write down all these laws because we are familiar with them already from the function case. Maybe just to recall the squeezing theorem, because this is an important result. Okay, so if you have three sequences, A an, bn, and cn, and bn is like squeezed between an and cn. If you know that the limit of an as n tends to infinity exists and is equal to the limit of cn as n tends to infinity, all of them exist are equal to L, then you can conclude from this situation that this limit here exists as well and is equal to L as well. Okay, so this is just the same result as for the function case. Okay, so the important thing is actually you should read this in like this contains two important informations. The first information is, okay, if you know that this limit and this limit here exist, okay, then this limit here will exist as well. Okay, I should say if this limit here exists and this limit here exists and they are the same, then this limit here exists as well and is equal to the L as well. So this contains actually two informations. Okay, and using these theorems, we can more or less use the same approach as for functions in order to figure out whether a sequence is convergent or not and to find its limit. So just to look at some examples. Just to see how this systematically works, of course there is no big difference to the function case. So if we look once more at this example here, okay, then now we know that, okay, we know already the trick. We divide both by 1 over n. So we have 1 over 1 plus 1 over n. Okay, and now since all the limit laws hold, so we can the limit of a fraction is the limit of the numerator divided by the limit of the denominator. So we have this is the limit n tends to infinity of 1 over limit n tends to infinity 1 plus 1 over n. And we have also the rule that the limit of a sum is the sum of the limits. And the limit of a constant is equal to 1 over 1 plus, and this limit we just figured out is 0, so what we get is 1. So this is just to show you once. Of course, it's trivial, but it's just to show you once, okay, how we systematically compute such limits, okay. Actually, everything started from the epsilon delta definition, okay. But we proved, I haven't done it really, but we proved a couple of theorems, and those theorems are helpful because we can just refer to the function case, okay. So also like using the L'Hopital would work here, okay. But of course you're not going to differentiate here the numerator and the denominator, okay, because this is a sequence, okay. We haven't introduced the derivatives for a sequence, okay. So if you use the L'Hopital here, of course it's like you differentiate here, you get 1. You differentiate here, you get 1, okay. And this is the limit, okay. But you are not allowed to apply here the rules of the L'Hopital because it's a sequence, okay. So what you do is you look at the function f of x is equal to x over x plus 1. You use the L'Hopital for this function, and you use the theorem I told you in order to deduce the limit here. It's just to make this once and for all clear. Okay, so any questions to this? I guess there shouldn't be any questions because this is like very similar to what we have done last semester and also what you have maybe learned already in high school. Now, just one more example to remind you on the importance of the squeezing theorem. So for instance, this one. Okay, so for this one, we will first, because you see that the numerator is given by the sign, so the sign is bounded by 1. So the obvious idea is to look at the absolute value of the sequence. Now the absolute value of the sequence is clearly larger or equal than 0. And if we plug it into the sequence, actually here we can forget about the absolute value. then you see we can use the estimate smaller or equal than 1 over 1 plus square root of n. Now, since as n tends to infinity, okay, so as n tends to infinity, this will tend to 0. This here will tend to 0 as well. Okay, so we can use the squeezing theorem. So this limit here, the limit of the absolute values of an will exist as well and will also approach 0. Okay, so we have proved that the limit of the absolute values of an as n tends to infinity is equal to 0. And because of the theorem which I told you before, this implies that the limit of an as n tends to infinity is equal to 0 as well. So this is the precise way to argue here. Okay, so this is a simple example. Of course, for these examples, you can go back to functions. Okay, like this. If you want to handle this limit, you can consider the function 1 over 1 plus square root of x. And for this function, we know already how to treat it. And then you use the theorem I showed you before. But sometimes this is not possible, in particular if there are more exotic sequences involved. For instance, this one. Okay, so this is slightly more exotic. The problem you have here is, okay, you cannot, if you're interested in this limit, okay, it's not possible to find here a function. So if you want to find a function which it's evaluated that the positive integers is equal to the sequence, okay, for the denominator it's possible x over x, but for this one, okay, it's not really possible. Now, there exist functions, okay, but we do not understand them very well. So here, in this case, we cannot use that we pass on to a function. We use what we know for functions. We go back to the sequence. We cannot use this approach here. In such situations, normally, it's kind of you have to use some different tools. Here, the squeezing theorem will work well. Because you see that this, if you look at the sequence, it's clearly larger or equal than 0. Now, you can write this as, okay, so here the n factorial, you have 2 times and so on times n. And here you have n times. Which is good because, so here you have n times 1. I should actually write here 1. So this is obviously smaller or equal than 1 over n. So, and you know, and this here tends to 0 as n tends to infinity. This tends to 0 as n tends to infinity. So by the squeezing theorem, this sequence here tends to 0. This is already, this is almost trivial, but this is quite remarkable because this tells you that this sequence n to the n grows faster than n factorial. Okay, so if you want to compare the growth, the speed of growth, because as n tends to infinity, n to the n, of course, goes to infinity. As n tends to infinity, n factorial also will go to infinity, will get larger and larger. Okay, if you want to understand, okay, which one of them is growing faster to infinity, here this tells you that n to the n is growing even faster to infinity as n factorial. Okay, so actually, it's, limits of sequences tell you something about the growth behavior. If you want to compare the growth behavior of 2 sequences, tell you something about this. Okay. Now, an important sequence for us is this one. R to the n. Now, if the exponent here is an integer or a positive integer, then of course r is also allowed to be negative. Okay, so here r can be everything. R can be any real number. Okay. If you replace n by x, it's not allowed that r is negative. But if you just consider exponents which are positive integers, then r can be everything. And we are interested in, okay, how about the convergence of this sequence? Actually, this is, of course, it's trivial, but let's just check for this sequence once more how this fits in our context. Okay, so what you will do is you will divide here. So if you wanna discuss the convergence of this sequence, you will divide this first. You will first naturally consider the case where r is larger than 0, because in this case you can replace or you can generalize this sequence to the function f of x, which is r to the x, which makes perfect sense here. Now, you see that the limit of f of x as x tends to infinity is equal to, now 0 if r is smaller than 0, larger than 0 and smaller than 1, then 1 if r is equal to 1, and infinity if r is larger than 1. Okay, and using our theorem, the theorem which I showed you before, okay, you can use this, because if you evaluate this function at positive integers n, what you get is just this sequence. So you can use this in order to draw conclusions about the convergence of this sequence. So from this you immediately get that the limit as n tends to infinity, r to the n is equal to, now just the same behavior, 0 if r is then 1 if r is equal to 1, and infinity if r is larger than 1. Here I should maybe mention the result which I showed you before. If you have a function f of x, you define a sequence an as f of n, then I claimed that if the limit of f of x as x tends to infinity is equal to L, then the same holds for the sequence. Okay, it's also true if the limit is infinity. Okay, also this case is included, so that's why I can draw this conclusion here. So this is for the first case. This explains the first case. Now the second case. I should write here case 1. Now the second case would be the case where r is larger than minus 1 but smaller than 0. 0 again is trivial, because here of course you have convergence. For this case, okay, we will look at the absolute value of this sequence, because okay, so if we look at the limit, so we will first consider the absolute value. Okay, now okay, so this is the limit as n tends to infinity, absolute value of r to the n. And if you look at this, this corresponds to this case here, because if r is between minus 1 and 0, you take the absolute value, you are here, so what you get is 0. And using one of our results before, this will imply that the limit as n tends to infinity of r to the n is equal to 0, also in this situation. And for all other situations, so the remaining situations is r is smaller or equal than minus 1. So here actually you can look at, if we look at the case r is equal to minus 1, so here we have an is equal to minus 1 to the n. Now, of course you know that this sequence is divergent, not convergent, okay? But maybe as an exercise you can try to use the epsilon delta definition to prove that this sequence is divergent. Okay, this is something you actually have to do in order to prove that this sequence is divergent. Okay. Now the reason why this sequence is divergent is there's no chance that this sequence is getting close to one number, because it will be for all it will be close to two numbers actually, minus 1 and 1. Okay, infinitely often. So that's the problem here. And if r is even smaller than minus 1, you have the same problem. Okay, so yeah, divergent. This should be enough here as explanation. We know already last semester limits of functions that proving divergence is proving that the limit does not exist is not so easy sometimes. Okay, because you actually have to prove that no number is the limit of the sequence. Okay, and you have to use the epsilon delta definition to do this precisely. Okay, but everyone will believe me that this sequence is divergent. Okay, so in order to summarize, the limit as n tends to infinity r to the n is convergent if r is larger than minus 1 and smaller or equal than 1, and divergent otherwise. Okay, this is something actually you know already from high school, but this is just to tell you, to show you once more how to use the theorems I showed you before in order to systematically derive this result here. Okay, but for the subsequently treating limits of sequences, we will, of course, we will not go back to the epsilon delta definition. What we will just use the tools we have already learned last semester, and the connection I just introduced. This is just to make you understand why the author, if you read this chapter 11.1, why the author is introducing those results. Okay. So any questions to this? Now maybe I spent too much time because this is actually I talked about this already last semester. If you remember, before I was introducing the integral, I was introducing most of the things I talked now in the first 50 minutes, but maybe a little bit more quick. And it is a good time because this is a new semester. We are just starting, so we can start a little bit slow, then gain speed. Of course, I understand that this everything is already quite clear with your high school knowledge, but you should understand the difference. There's also the reason, because this looks now much like I have discussed the sequence R to the n looks much more complicated than how you have done it in high school. Okay, but the difference is that the results I used are all precise, and I'm going back always to the epsilon delta definition. At least implicitly, because in the results which I haven't proved, the proof will we will use the epsilon delta definition. We will maybe make a few, in the assignments we will have a few examples where you have to check limits using the epsilon delta definition. I think in our textbook you also find a number of such assignments. Now, actually, everything I talked about is so far is just useful for sequences which are given by an expression. So where the an is given explicitly, like for functions where we have given the function by explicit expression. But as I told you, there is also another way to describe sequences, namely recursively. Now, what we have done so far is not useful in order to prove that, for instance, if you have given some sequence recursively, that this sequence is convergent. Okay, this doesn't help. Normally, unless you can find an exact expression for the sequence. So for sequences which are given by recurrences, okay, we will need other tools in order to figure out that in order to be able to figure out whether such a sequence is convergent or not. And this is the next point I want to stress. So first of all, you find actually this I don't have to write on the blackboard. You find in our definition in our textbook you find the definition which is increasing and decreasing of sequences. This should be pretty clear. It's something you have also learned in high school. So a sequence is increasing if it's getting larger and larger, decreasing if it's getting smaller and smaller. It's like maybe it's a good time to stress once more, or maybe I should just to make this clear. This is called increasing, this property. Okay, and this property is called non-decreasing. Okay, so just to stress this once more. Okay, because sometimes this is always confusing because other textbooks maybe have another notation. For other authors, maybe this is called increasing and this is called strictly increasing. Okay, but for me, this is called increasing and this is called non-decreasing. Okay, so non-decreasing does not have anything to do with decreasing. It's not decreasing. Okay, just to make this clear. So a sequence will be called increasing if it has this property here, decreasing if the same property but with the inequality in the other direction, and a sequence will be called monotonic if it's either increasing or decreasing. Now, for instance, this sequence, okay, obviously decreasing. Because if you make the n larger, you get the terms are getting smaller and smaller. Or this sequence here is also very simple. It's of course increasing. Okay, now for instance this one. Okay, this is another example. Now if you want to figure out whether such a sequence is increasing or decreasing, normally one way to do the first thing you sometimes might do is you just check the first few terms and look, okay, does the behavior look like increasing or decreasing? Then you get many times you get a conjecture. But here for this is pretty easy, because the obvious trick is you look at this function here. Because for functions we have much more tools in order to understand whether a function is decreasing or increasing. We just use differentiation. But for sequences we do not have those tools. So we will first look at this function, and this sequence is just this function but sampled at the positive integers. So for this function we can easily figure out, we can easily discuss the monotonic behavior of the function. We just look at the first derivative. Okay, so you see that this is smaller than 0 if x is larger than 1. Okay, so which means that this function here is decreasing as x is larger than 1, from 1 to infinity. Okay, and of course this will imply that this sequence is decreasing. Okay, so this is the most easiest way to see that this sequence here is decreasing. Okay, you see the reason why we pass to functions, because for functions we have learned a lot of tools last semester. We can systematically apply these tools, and this works for quite a lot of sequences in order to prove that they are decreasing or increasing. And but you know, another way to which is most of the time also possible, is like you use induction to prove it. If you have first you make a guess, you use induction. This is always another way to prove whether a sequence is increasing or decreasing. But if a sequence, this does not help if the monotonic behavior changes. For instance, if the sequence is first increasing and then decreases. If you look at the corresponding function, if it's possible to find the corresponding function, much more easier to find such behavior than looking at the problem where this is kind of, because you can also look at this as a function where the domain are the natural numbers. Okay, so this is monotonic behavior. Now, the next thing which is introduced in our textbook is kind of is bounded. So a sequence would be called bounded from above. If you can find some bound m such that this holds for all n, so this is called bounded above. And if you can find some small m such that this relation holds for all n, then we will have bounded below, from below. So here you have an upper bound, here you have a lower bound, and the sequence is called bounded if it has both, if it admits both the upper and the lower bound. So for instance, this sequence here will be bounded because it's decreasing, so it will certainly be bounded from above. But it's also bounded from below, larger or equal than 0. So this sequence will be bounded. This sequence here will be bounded from below, but not bounded from above. So this sequence is not bounded. Okay. That this sequence is bounded actually is no coincident because maybe this can be stated as a theorem. Every convergent, so if f is convergent, if an is convergent, then an is bounded. Okay, so this is always true, that if you have a sequence which is convergent, such a sequence will always be bounded. This I'm not going to prove it precisely. You can try to prove it precisely, but just to make this, just to make you understand why this is the case. So assume that the limit of a of n as n tends to infinity, because we assume convergence, so that the limit exists, it is equal to L. So assume that, okay, limit is L. Now, for every epsilon, so we can, for instance, we choose epsilon to be equal to 1. Okay. So for epsilon is equal to 1, from a certain index on, all the an will be inside this epsilon interval. So outside you will have just a finite number. Okay, so the sequence is bounded because you just move the boundary, okay, till you catch all the finite terms which are outside. Okay, so more or less this is the reason why every convergent sequence is bounded. So this sequence will be automatically bounded when because we know that this sequence is convergent. Okay, and now the important message, and this I guess some of you have heard already in high school, but one of the important tools we are going to apply later on, which will be a very important tool for proving results concerning series, is the so-called monotonic sequence theorem. Every bounded convergent monotonic sequence is convergent. So this is called monotonic sequence theorem. This is maybe something you have learned in high school, something which should be pretty obvious. So, in particular, maybe in this form, it's stronger than it's really necessary. So, for instance, if you have an increasing sequence, okay, if a sequence is increasing and it's bounded from above, then it will be convergent. And the same for if it is decreasing, bounded from below, it will be convergent. Okay. Now, these theorems, everyone will accept this. This should be an easy result. But if you look, I'm not going to prove it, but you can find the proof in our textbook. The proof actually is not so easy of this result here, and I mean it's not complicated, but you need some of the so-called. If you look at the proof in our, you can read it on your own if you are interested. The proof uses some of the completeness axioms for the real number. So if you want to prove something like this here, essentially the problem we have at the moment is that we have never defined the real numbers precisely, and this is what we should have to do first in order to prove such a theorem. So if you look at in the textbook, you will see that for the proof, because you can find the proof there, they also use this so-called completeness axiom. But just look at the proof if you are interested. Otherwise, just accept this as a result, which should at least intuitively should be very clear. Because once more, if a sequence is like increasing, okay, bounded from above, okay, then the sequence should be convergent. The problem in proving something like this, okay, is like what is the limit? Okay, so if you have such a sequence an which is increasing and bounded from above, this is the only thing you know. Okay, now if you want to prove the sequence is convergent, okay, you first have to have a guess for the limit. Okay, now what is the limit in this case? Not so clear. Okay, so you need some tool to produce the limit. And if you look at the proof in the textbook, this is provided by the. Everything is necessary. Okay, so the conditions are necessary. If you drop, for instance, monotonic, okay, then the theorem will not hold, because if you look at this sequence, okay, this sequence is bounded, but not convergent. Okay, so here this is a counterexample that I'm not allowed to drop monotonic. Okay, and of course I'm not allowed to drop bounded as well. Okay, because we saw already an example, this one. Okay, so if I drop this one, then the result is wrong as well, because this sequence is monotonic, but not convergent. Okay, unless you accept that this here is convergent as well. Okay, if you accept this as convergent as well, if you say, okay, this is convergent, then, because in some textbooks, if you look at other textbooks, you sometimes see this result stated as every monotonic sequence is convergent. Okay, but then for the author, this is part of the divergent of the convergence definition as well. Okay, but for us, it's not. This is not the case. It's just if you look at other textbooks that because you will later on you will learn other theories and maybe it will be done differently, just to make you aware of something like this here. Okay, any questions? Okay, so let's make a break of 10 minutes. I'm sorry, I was not watching at the time. Look at some examples that you see how to apply the monotonic sequence theorem. Now, I said already that actually with the tools I have shown you before, it's not possible to handle convergence of sequences which are given by recurrences. So one of such a sequence, for instance, this one, and am plus 1 is equal to so for instance this sequence. Okay, you have given now a sequence given by a recurrence relation, and you wanna the question is, okay, is this sequence convergent? Okay, so maybe in high school you have already done something like this here, maybe. So this is this is asking the question, okay, if you look at this kind of thing, and you go on forever, okay. So does this expression has a value? Okay, it's the same question. Okay, so you want to know that this is the same as to ask for the limit here. Okay, does it exist? By the way, if I do not write large enough, okay, please tell me from behind, because I saw that many students wrote in their evaluation that I'm not writing very beautiful on the blackboard. This is actually true. I admit this is true, but there is no chance that I can write more beautiful. This is already the beautiful version of my handwriting. So if you cannot read, okay, just feel free to interrupt me, and I will write more clearly. Okay, I try to write as readable as possible. So this is really very readable compared to my handwriting. Okay. Unfortunately, it's not really possible to write larger because the blackboard is too small, and I'm not large enough to reach the upper part. Okay, so what we want to do is we want to discuss, okay, whether this limit here exists or not. Now, the problem we have here, compared to the previous examples, is that an is not given by an expression. Okay, an is given by a recurrence. Now, for such examples, normally the first thing to do is to compute some of the values. Actually, the first one is, then the second one is, I didn't bring a calculator, so I don't know. This one is 1.4. And who has a calculator? Who can help me to compute this one? $1.885. So larger than this one. Okay, so this is the import. And now, someone please help me to compute this guy. 1.96. Okay, so already from here we could guess, maybe not, we haven't computed too many terms, but from here we can already kind of make the conjecture that the sequence looks like increasing, okay? And as for an upper bound, okay, of course it's not really, we have to compute more values in order to understand, okay, what is an upper bound. But we can try something like 3 maybe. 3 should work here in this case. Okay, so normally if you want to discuss the convergence of such a sequence, the first step is to compute some values, okay, then to make a conjecture. And then the second step is to prove the conjecture by induction. Okay, so here our conjecture, our guess, an is increasing and smaller equal than 3. So actually this is my guess. Maybe this guess is wrong, but we can check it by induction. If the induction proof does not work out, we just make it larger. Okay. So now, so this is the first step. Okay, guessing. You compute some values. You guess the behavior. If you see that the behavior is like increasing and bounded from above, if we can prove this, it's very good because then we know convergent. Okay, because of the monotonic convergence theorem, which tells us that actually, if you look at the version in our textbook, the version in our textbook is a bounded and monotonic sequence is convergent. Okay, but I told you the important thing about this theorem is increasing at the upper bound and decreasing or decreasing at the lower bound is enough for convergence. Okay, so if we want to prove that this sequence sequence is convergent, okay, we need first such a guess. If there is such a behavior, okay, we just prove this behavior by induction, and then we can conclude from the monotonic sequence theorem that we have convergence. And computing the limit is an easy. Why is computing the limit easy? Because you just look at this here and take limits on both sides. So if you know that the limit exists, okay, then the limit will be something like L, and you see from this here immediately L is equal to square root of 2 plus L, and you use this in order to compute L. Okay. But first, you have to prove convergence. Okay, it's different problems. Computing, proving that the sequence is convergent, and computing the limit. Okay, are different steps. Okay, so you do it differently. Now let's prove this guess here. Let's first prove this one here, smaller equal than 3. So what I claim is, my claim is smaller equal than 3 for all n. Now we prove this by induction, okay? We see that a1, okay, a1 is the square root of 2, is smaller equal than 3. Okay, that's okay. So the induction step is already over. Now we go from, this is called the initial step, sorry, this is not the induction step. Okay, this is called the initial step, the first step. And now comes the induction step. So you know that the claim is true for n, and you want to prove it for n plus 1. This is essentially the induction step. Okay, so what we know is that an smaller equal than 3. Now, this in particular means that an is smaller equal than 7. Okay. Now, it will become clear in a minute why I want to do this, because that's the reason why I guessed 3 here. Because now you add 2. And now you take the square root. Okay. But if you take the square root here, you get an plus 1. So you see that an plus 1. Okay, so we are done. Okay, because we have concluded, if we know that an is smaller equal than 3, we can prove that an plus 1 is smaller equal than 3 as well. Okay, so this proves by induction that an is smaller equal than 3 for all n larger equal than 1. If you have if you have to solve an exercise like this, you should really do it like this. Okay, so write clearly what you want to do and write every step of the induction proof. Okay. Normally, very often, okay, for the induction step, maybe I should just try, but this is not so essential. But for the induction step, very often this is our guess, okay, and we will proceed in this direction. Okay, we try to this is our guess, and then we try to prove to use this here in order to prove the guess. So normally we will often start from here. Okay, but it's not so natural because actually you have to go from n to n plus 1 and not from n plus 1 to n. Okay, that's why I wrote it like this here. It looks more complicated, a little bit more complicated, but you can also do it the other way around and then just reverse the process in order to write it down. Any questions? Which one? There are many. This one? This one? This one? This? This is 7. This is like the European version of 7. The Americans maybe do it like this here, right? Like the European version is like the Chinese one, just the other way around. You see? Okay, so we still have another guess. This here, increasing. Okay. Now, also increasing, we are going to prove it by induction. So claim for all n larger or equal than 1. Okay. Now, so we again you have the initial step. Okay, so this one. Okay, this we just verified. Okay, this is okay because we computed A1 and A2. So the initial step is always easy. Now the induction step. Okay, so we have to go from n to n plus 1. So we know that this is true here, and we want to prove that an plus 1 is also smaller or equal than an plus 2. Okay, so what we do is, okay, we have an is smaller or equal than an plus 1. Okay, so we can add 2. So we have an plus 2 is smaller or equal than an plus 1 plus 2. And we can, on both sides, take the square root. So the square root, so an plus 1, which is the square root of an plus 2, will be smaller or equal than the square root of an plus 1 plus 2. Okay, and this is equal to an plus 2, and we are done. Okay, because here you have the. Okay. So if you want to prove something like this, you should really spend a little bit of time, and you should try to learn it, to do it systematically. Okay. So first your guess, and then use induction to prove it. Okay. I see quite often from like last semester, some students just compute the first few values, then tell me increasing and bound it, and then just use the monotonic sequence theorem. But it doesn't prove anything if you just look at a few values. You still have to use induction in order to fill in the gaps, to really prove it. Okay, so from this now, so any questions to this? So from this, we can now conclude that the limit of a of n as n tends to infinity exists, and is equal to L. Okay, it's equal to some L. And so the first step is always to compute to prove the existence of the limit. The second step is then to compute the limit. Okay, so we look at the sequence an plus 1 is equal to the square root of 2 plus an. Now we know already that the limit exists. Okay, so this means we can take the limit here on both sides, and we get that L is equal to square root of 2 plus L. Okay, which is then equivalent to L squared minus L minus 2 equal to 0. Okay, and this here, L minus 2 times L plus 1 is equal to 0. And from this we get that L is equal to 2, or L is equal to minus 1. Okay, but we can forget about this one because our sequence. So we can forget about this one because our sequence is always positive. So there is no chance that our sequence converges to this point here. Okay, so L is equal to 2 will be the limit. Okay, so this means that this guy here, 2 plus square root of 2 plus square root of 2 plus and so on is equal to 2. Maybe the guess is that if you replace 2 here by any a, which is larger than 1, maybe there is a here. You can try to prove. Just a guess. Maybe it's true. So you can try to replace the 2 here by any number which is larger than 1, and can check whether the answer will be a here. Okay. So any questions to this? So if you wanna once more, if you have a sequence which is given by recurrence, you want to prove that the sequence is convergent and find its limit. Then first you have to compute. You check some of the terms. Okay. Then from the terms you will normally get the guess. Okay. From the terms you will very often see that the sequence is either increasing or decreasing. If you have such a guess, you prove it by induction. And you need also, if increasing, you need bounded from above. If decreasing, you need bounded from below. Okay. You prove also, you guess a bound. You prove it by induction. Then you get that the sequence is like here increasing and bounded from above. You can use the monotonic sequence theorem in order to conclude that the limit consists, that the limit exists. And if you know existence, then you just use the relation in order to compute the limit. This is more or less how to solve such exercises. In our textbook, you find many, many others which are similar style. Maybe let's do one more. Two numbers, a and b. Now, what we are going to look at is we define a1, which is a plus b half, the arithmetic mean, and we define b1 as the geometric mean of those numbers. Okay, and we know that the arithmetic mean is always larger than the geometric mean. This is something you have learned in high school. Now, so this is, you can consider the sequence. So maybe I should, the first term here of a0 is a, and the first term of the sequence b is b. Okay, and now you use a construction which you go on like this. Okay, so you define an plus 1 as, okay, you choose an plus bn half, so the arithmetic mean of the previous two. And this will be larger or equal than the geometric mean of the previous two. Okay, now if you look at those numbers, okay, so you see that the an plus 1, now, because you have already the relation that an is, you see here an plus 1 must be larger than bn plus 1, but you have also that an is larger than bn. Okay, so you will see that this one, because bn is larger than an, so this will be larger than an, and you see that bn plus 1, because an is larger than bn, so you see this is larger than bn. Okay, so you see from this that these, if you look at the sequence a, the a sequence, okay, the a sequence starts at a0, it's larger than a1, and if you look at this, okay, it's decreasing. Okay, but you see that if you look at the b sequence, the behavior of the b sequence is in the other direction, increasing. Okay, so you see that the a sequence in particular is decreasing and bounded from below. So the limit an as n tends to infinity exists. Okay, because this sequence of the an is decreasing and bounded from below, and the sequence of the bn is increasing and bounded from above. Okay, so also this limit here exists. Now, of course, it might be different, okay? So this limit here, let's say this limit is equal to some alpha. Let's say this limit is equal to some beta. Okay, they might be different. Now, in order to figure out, okay, those limits, we can, for instance, look at this relation here. So from this relation, by taking limits now, so we have an plus 1 is equal to an plus bn half. Now, by taking limits, we get alpha is equal to alpha plus beta half. Okay, but this will imply that alpha is equal to beta. So actually, those two numbers are the same. Okay, so there is one number sandwiched between all of them. Okay. Now, you know from high school that this here is called the arithmetic mean. Okay, and this here is called geometric. This is called geometric mean of the two numbers a and b. Okay, so if you use such a procedure, okay, if you start with two numbers, you compute first the arithmetic mean and the geometric mean, and then for the new two numbers, you again compute the arithmetic, geometric mean, and so on. Okay, you will get, if you just look at the arithmetic means, you will get a sequence which converges to one number. Okay, and if you look at the geometric means, you will also get a sequence which converges to the same number. Okay, that's why this number here was already, this is one of the exercises in our textbook. This number was already considered by Gauss, and is called the arithmetic geometric mean, both arithmetic geometric mean of the number AB. Okay, this is another interesting example, and here you see as well how to use the monotonic sequence theorem. In the next next couple of sections, we'll play the same role as the, for instance, mean value theorem has played in order to investigate relations between a function and the derivative. So we'll be so this theorem will be one of the main tools in order to understand what comes next, namely series. So next we are going to talk about series. So essentially, you start from a sequence. You have a sequence. And so on. And what you do is you just sum it up. You try to sum it up. And so on. And this is called a series. Now, if you have an infinite number of terms, summing them up doesn't necessarily make sense. Or at least we should clarify first what is the meaning of something like this here. 1/2 plus 1 over 4 plus 1 over 8 plus and so on. So what is supposed to be the meaning of this? You know this, I guess you know this from high school. The Greeks have rejected having objects like this here. It's like there are the famous paradox where they said this is impossible because this is like you try to, someone is standing in front of you and you walk first half of the distance, then you walk 1/4 of the distance and so on. So the Greeks actually used this in order to say motion doesn't exist, okay, because you never reach. Okay, but the contradiction is because the Greeks haven't had the notation of limits. Okay, now in order to give something like this sense, okay, you need a notation of limits. Now, the way we give this kind of expression sense is, okay, obviously we do not carry out the whole summation. Okay, we first just add the first term, then the first and the second, then the first, second, third, and so on. And in doing this, you naturally get a sequence. Okay, so this sequence will start with, so first 1/2, then 1/2 plus 1 over 4, which is 3 over 4. And you go on like this. And you will see that if you do this n times, you will get this here. Okay, so this sequence which you see here, by adding up the first n terms, will converge to 1. Okay, and because this sequence is convergent, we will say this guy here exists, and the value is equal to 1. Okay, so it's not that we really sum up an infinite number of numbers. It's not possible. Okay, we look at the corresponding sequence, the sequence of the sum of the first n terms, and we discuss convergence of this sequence. And if this sequence is convergent, we will say that this guy here exists and is equal to, in this case, 1. Okay, so and something like this is called a series. Okay, so this will lead to this definition. So normally we use, of course, the sum notation. So this kind of object, okay, is called convergent. If we look at the so-called partial sums, now the index is a little bit awkward, so j from 1 to n, aj. So this is called the partial sums. Partial sum of the first n terms. If this and this will give us a sequence. So if this sequence is convergent, then the series will be called convergent. Okay. Otherwise, the series would be called divergent. So actually, the question whether a series is convergent or not just boils down to convergence of sequences. Okay, but the sequences are a little bit more complicated because you look at such partial sums. Okay, otherwise, it's called divergent. Now, in case of convergence, okay, the limit of this sequence is called a sum. Okay. It's not really, maybe I should stress this once more, it's not really that we sum up here, okay? It's just that we look at the corresponding, at the natural sequence of sequence of partial sums, and if this sequence converges to a sum, to a limit, this limit will be the sum of the sequence. So we will write of the partial sums is equal to S, then we write the value of this series is equal to S. Okay. This, I guess, you have heard already in high school. This is the basic definition from which we are going to start. Now, the most famous example for a series is this one. Now this is also called geometric series. This is one of our most important toy examples. This is also what you have learned already in high school. So for this series is very convenient because it's easy for this series to discuss whether the series is convergent or not, and also in case of convergence to find the value. So you all know I'm not going, because you know this trick here. So I'm not going to recall it. So you know that you have this value and convergence if the absolute value of R is smaller than 1, and divergence in all other cases. Okay, it's easy to prove. You know this usual trick. If you want to prove convergence of a series, so the only method we have so far is we really look at the partial sums. Okay, so for this guy, okay, you have to look at you have to add up the first n terms. But here you are lucky because you can find an expression, you know, by multiplying with R and then subtracting and so on. You can find an expression. So in this case, you are lucky because you can find an expression for the Sn, which is normally just given by a sum. Okay, and because of this, it's easy to discuss convergence of this particular series. Okay, now. There are also other examples where it's not complicated to figure out convergence, like this one. like this one. Okay, now for series like this here, the trick normally is okay. You use what we called partial fraction expansion last semester. So because this here you can write as 1 over n minus 1 over n plus 1. Okay, so this makes it easy to discuss the partial sums, which is the sum j from 1 to n, j plus 1. So you can write this as the sum of j from 1 to n, 1 over j minus 1 over j plus 1. Okay, and now you know, okay, this is the usual trick. So you have 1 minus 1 half, then you have plus 1 half minus 1 over 3 plus, and you move on like this. And the last one is 1 over n minus 1 over n plus 1. And you are getting lucky now because those all cancel. Okay, also this one cancels. The only terms which remain is this one and this one. Okay, which is a very good situation because in this case, which means you can get an expression for Sn, and whenever you have an expression for Sn, it's easy to discuss convergence. So you see here as n tends to infinity, this converges to 1. So this series is convergent with sum 1. Okay, I just want to, any questions to this? I just want to stress that because I see this every semester and I see this mistake every semester, and I want to avoid seeing it this semester. Okay, so I see very often that students argue like this here. So I give them such a series or a similar one. Now, okay, they break it into 2 parts. Now they write 1 minus 1 half plus 1 half minus 1 over 3 plus 1 over 3 plus, and so on. And now they say, okay, I can cancel. Okay, so the value is equal to 1. Now I do not like this kind of reasoning. Maybe you have done this in high school, but I do not like it, and it's not true. It's not correct as well. Okay, you understand why? This is not really the reason. The reason is because you actually, if you have a series, there are 2 questions related. The first question is the series convergent or not? The second one, if the series is convergent, what is the sum? Those 2 questions are normally different. So here, for this kind of reasoning, you assume already that the series is convergent. Then you can do this. Because an easy example is this one. Then I look at this one. Okay. Now this one is okay, 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on. And I do the same. Okay, so for instance, I cancel this one and this one and this one and this one and so on. So the value is 1. It's not true. Because I could also cancel this one and this one and this one and this one, and the value would be equal to 0. Okay, but 0 is not equal to 1. So there's kind of a problem here. Okay, so this kind of reasoning was like in the 18th century, okay, when the convergence of series was not very precise. This was done in the 18th century. So people have done this and say, okay, this proves that God exists, because from 0 you can create something. Okay, of course this reasoning is not true. Okay, because what is missing here for this reasoning, what you do not consider here, okay, is convergence. So first you have to consider convergence. Because this series is convergent, I proved it just by looking at the partial sums. Okay, so if you know that this series is convergent, this is correct. But the reason why this fails here is that because this series is divergent. Okay, so just to make this clear, because I see this every semester, and it breaks my heart to see this. One last one, this one. Now, if we want to discuss the convergence of this series, okay, again, the only method we have so far is looking at partial sums. Okay, so we have to discuss the behavior of the partial sums. Now, you see here, for instance, if you look at this one, S2, now S2 is equal to 1 plus 1/2. Okay, now the next one, let's look at, we do not look at S3, let's immediately look at S4. So S4 is equal to 1 plus 1/2 plus 1/3 plus 1/4. Okay, but if you look at those two terms, then 1/3 is larger than 1/4. Okay, so you can write this as it's larger than 1 plus 1/2 plus, and those two terms you can merge together. So this is also a 1/2. Okay, because this term is 1/3 is larger than 1/4, and those two add to 1/2. Okay, so what you get is 1 plus 2/2. Maybe it looks a little bit awkward the way I write it, but it will be clear in a minute. Now, if you look at S8, okay, 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. Now again, I group, okay, so I look at these two, and I look at this, the whole group. Okay, I replace this one by the last one, and I replace here in this group every term by the last one. Okay, then I get this is larger than 1 plus 3/2. Okay, so you see that this easily leads to the conjecture that if you look at the partial sums where you have here 2 to the n, okay, that this is larger than 1 plus n/2. Okay, so this is just a subsequence of the sequence of partial sums. But you see that as n tends to infinity, this will tend to infinity. Okay, now, of course, this will imply that Sn does not converge. It's not convergent. Okay, because you see that if you look at the subsequence, okay, the subsequence will go to infinity, so no chance that Sn is convergent. Okay, maybe this here, if you look at if you consider sequences for the first time, you have to think a little bit about it. But it's, if Sn would converge to some limit, okay, you can find the epsilon interval around the limit such that almost all terms are inside the epsilon interval. No chance, because the subsequence goes to infinity. This means, okay, Sn is not convergent, so we have just proved that this series is divergent. And this is a famous series, so it has its own name. It's called harmonic series. Okay, so the harmonic series is divergent. Okay, now so if we look at series up to now, the only way we can figure out convergence is by really looking at the partial sums at the sequence, trying to find an expression for it, or using such techniques in order to prove that the limit does not consist. This would be a little bit complicated for all series, because like if you look at the series, okay, not this one, but for instance, if you add this one, if you add the square, if you look at these partial sums, it's very hard to sum them up. So you just have this expression here. Now, how to prove that this sequence is convergent? We will find roughly speaking, the next 2 weeks we will discuss this problem, and we will find quite a lot of convenient tools in order to figure out whether such a series is convergent or not. Apart from this, the question of convergence is more easy, we will discover, to handle than actually finding the value. For instance, this series is convergent. This was known quite a long time ago, but it was very hard to find the value of this sequence, of this series. Okay, but I will talk about more about this next time. So any questions? If not, then that's it for today.